Hello everyone, I am Rudraksha Chouhan and this is my computer organization and architecture project on the Sun UltraSPARC processor. In this presentation, I will be taking you to the complete case study of this processor, including its architecture overview, instruction set design, pipeline structure, memory hierarchy, and specialized features. Towards the end, I will also demonstrate a simple factorial program written in the Spark assembly language running in a simulator to show the output. So let's begin with the first section, the architecture overview. The Sun UltraSPARC is a 64-bit RISC-based architecture which was developed by the Sun Microsystems in 1995. It belongs to the SPARC family, which stands for the Scalable Processor Architecture. The main idea behind the UltraSPARC was to deliver high performance with simple, efficient instruction execution. Being a RISC processor, it focuses on executing many small tasks, simple instructions, very quickly, instead of using large complex instructions like the CISC processors. It was primarily designed for the several workstations and enterprise systems, the kind machines that run large-scale computations and databases. The UltraSPARC architecture introduced 64-bit processing, which means it could handle larger integers and addresses much more memory than earlier 32-bit processors. Overall, its design aimed to achieve speed, scalability, reduced power consumption, three major goals of the RISC processors. Now, the key features and design principles. So as I told earlier that it follows the RISC principle, which makes it simple fixed length instructions. It has a load store architecture with 32 general purpose registers. And the register windows, it uses the register windows for fast function calls. And the processor is also pipelined, which allows the overlapping stages of different instructions similar to an assembly line, where multiple instructions are in progress simultaneously. Finally, it supports multiprocessing. So multiple UltraSPARC CPUs can work together in the same system, improving performance in server environments. Now coming to its instruction set architecture. So as I told earlier, it was based on a SPARC v9 ISA, which is a 32-bit instruction length. And there are three major instruction formats. Format 1 is used for call instructions. Format 2 is used for arithmetic and logical operations. And Format 3 is used to load and store operations. Spark also supports several addressing modes, such as the register addressing modes, immediate values, and the displacement addressing, where an address is computed on a base register plus an offset. The two interesting instructions in this architecture are save and restore, which are used to move between registers windows during function calls and returns. These features make Spark very efficient in handling nested or recursive functions, which is a key strength over traditional 6 processors. Now the data path and pipelining. So as you can see, the Spark uses 5-stage pipeline, which consists of the instruction fetch, instruction decode, execute, memory access, and write back. This pipeline allows the new instructions to start executing even before the previous ones finishes, which increases the throughput. UltraSPARC also supports the superscalar execution, which means multiple pipelines can operate simultaneously. In some models, limited out-of-order execution is also supported. The data path includes all the essential components, the program counter, the instruction cache, register file, ALU, and the memory unit. Together, these units allow the smooth instructions flow and efficient arithmetic and logical computation. So coming to its memory hierarchy, it is split in L1 cache, which is which stores instructions with 16 to 32 KB of size, and data which stores 16 to 32 KB of size. And it also supports virtual memory and advanced cache replacement policies that helps to optimize speed and reduce access delays. And the processor communicates with the memory using the 128-bit wide memory bus, which allows transferring large chunks of data per clock cycle. Overall, this hierarchy ensures that the processor spends less time waiting for data and more time in executing instructions. So coming to specialized features and parallelism, it supports symmetric multiprocessing, which means multiple processors can share the same memory space and work together efficiently. It also introduced the VIS, which is virtual instruction set, which was designed for multimedia tasks like image processing, video compression, and graphic rendering. These VIS instructions operate on multiple data elements simultaneously, similar to the modern SIMD, which is single instruction multiple data operations. Later, UltraSPARC models also provided the hardware support for virtualization, which allows multiple operating systems to run on the same physical machine. This combination of multiple processing and SIMD support and virtualization made Spark UltraSPARC are highly relevant for high-end enterprise and cloud environments. So coming to its historical significance and comparison, the UltraSPARC processor was launched in 1995 and quickly became the backbone of the Sun Microsystems enterprise server and workstations. At that time, it was competing with the processors like Intel Pentium Pro, which used a CISC complexion instruction set computer design, while the Intel processors focused on compatibility with other software and complex instruction. UltraSPARC focused on efficiency per instruction, making it faster for scientific and engineering applications. Its RISC design also made it more scalable, meaning performance increased, more predictability with larger clock speeds and multiple cores. Historically, UltraSPARC played a crucial role in establishing RISC processors as a serious alternative to the CISC in the enterprise market. Now coming to its assembly code, which is a factorial code. So the factorial code, as we can see here, it is written here. And in this code, the number 8 is loaded into the 0 memory location, which is used as an input argument to the factorial function. The save and restore instructions create and destroy the stack frame from each function call, which is the part of the Spark register window mechanism. The call instruction transfers control to the factorial function, and the NOP following it executes while the branch is processed. This is due to the Spark's delaying branching's design. After computing the factorial, the result is returned to the 0 memory location and printed using the printf with the string format defined in the .rot data section. When it is run in a simulator like QEMU or Spark emulator, the output will be displayed. So as we are going to see how it works on a terminal. So we have opened our Ubuntu, and we are going to open the project which I have saved here. So this we will write this code to access our project. So we have accessed our project and we will see how many files there is. So we have two files, factorial.c and main.s. So let's go through both of them one by one. So we are writing. So we can see here is a factorial program. If n is equal to 0, return 1. Unsigned long f is equal to 1. For unsigned long I is equal to 1, 2 I less than n, I plus plus. Factorial is equal to factorial into I and return factorial. So this is our factorial program. And let's see what is in the main.s. Okay, so here is our program which is saved in the main file. Section text global main type main function. As we can go through the entire code line. So let's see what it does. So we are going to compile these both code written in the both files. So we are going to copy and paste this command here, as typing it manually will take a lot of time and time is less. Okay, so we are going to compile it. As we can see, the code is successfully compiled, and now we are going to print the output. So we are writing QEMU Spark 64, and let's just copy it. And okay, so as we can see, the program works successfully and it has printed the factorial of 8, which is 40320. That is exactly what I was trying to demonstrate with the assembly language code, that this is perfectly working in the UltraSPARC processor and in the QEMU simulator. So we can say that the Sun UltraSPARC processor represents a major milestone in the RISC architecture design. It introduced features like the superscalar execution, register windows, multimedia instruction sets, and multi-core processing support, which made it ideal for high-performance computing. Its clean design and scalability have influenced many modern CPU architecture that we use today. Thank you so much for watching my presentation. It's Rudraksha Chouhan signing off.